Okay, thank you and thanks for the organizers. So this is a joint work with Ville Kotovirta, and we are from VTT's big data team. And VTT is a governmental research organization with some 2,000 researchers, and basically all areas of technology, including the quantum technology, is highly topical now. Okay, this is the outline of my talk. So first I describe the Semeredis regularity lemma and regularity check problem, and then introduce Ising model for regularity check, and then a novel community detection algorithm based on those, and then some simulations and experiments with D-Wave machine, and appendix, if I have time. Okay. So this is how the D-Wave current version that we use looks with Chimera architecture. So it's finding solutions for this kind of programs, binary quadratic programs, and it's based on adiabatic theorem in quantum theory, and it looks like this. Okay, and the motivation of our work is to suggest probably a new hard problem that could be used in testing these devices, and it's the regularity check that is known to be co-NP complete decision problem, and maybe here you can find the hard instances easily, and it's easy to make in this quadratic optimization form without, you don't need any constraints, for instance. And a byproduct is this community detection algorithm. Okay, so first about this Semeredis regularity lemma. It's a major result in graph theory, but it has had many applications in other areas of mathematics and computer science. For instance, this celebrated green tau theorem is one example. So what is this Semeredis regularity lemma? It states that any large graph has this kind of partitioning of nodes into bounded number of sets in such a way that if you look at the links between these sets, they are called regular pairs. The links are almost as they were drawn at random, so there are no structure in this. So this regular pair is important for us. So if you are looking at it, the links between these pairs, it's like a bipartite graph where you have links only between two disjoint sets. Okay, and this regularity, epsilon regularity, as defined by the same tau that I mentioned, it's the most convenient formulation for us. It states that if you look at this bipartite graph and any subset of nodes, and then this kind of bound should hold where the epsilon is. Epsilon is some positive number, and actually in theorem it can be made as small as you wish. So D is the link density in the subgraph. For instance, here X and Y are the sets where you want to compute the density. E is number of links that join these two sets, and okay, and then you divide it by number of nodes in X and number of nodes in I, and you get some number between 0 and 1, and similarly for the whole graph. So meaning of this is that link density should not deviate much from in subgraphs, from the link density in the whole graph in this normalized way. Okay, so the left-hand side of this bound, I call it Gauss function for regularity check. It's an unofficial name, but anyway, it's like this. It's written in this form. Its meaning for some x and y is that it computes fluctuation of the fluctuation of the number of number of links from the expected one, and this expectation is computed from the if this graph was truly random, then this would be the link probability and how much it deviates from what would you expect in average. So this must be bounded by epsilon. And as a result, the range of this function defines whether the bipartite graph is epsilon regular or not. So if you can find minimum and maximum of this, you can solve this problem. But as I said, this problem is going to be complete, and there must be some difficult cases of finding minimum and maximum. Okay, I already said this. So for now on, we are talking about minimum. The maximum could be done in a similar way, but now we always have a minimum. And meaning of this minimum is that you try to find some denser subgraph where the fluctuation is upward, because this makes it negative, this whole function. Okay. And it's easy to write this L function as an Ising model. A is the adjacency matrix of the bipartite graph. Then you assign to each node a binary variable S. And these sets X and Y are encoded in such a way that a node belongs to X or I when the variable has value 1. And you can easily check that this L function can be written in this form. Otherwise, it looks like this. So the red links are counted, and these are the sets. So if all possible values are scouted, all sets X and Y are scouted as well. And so this is the community detection, because this minimum argmin L finds a dense subgraph, and communities are some dense subgraphs. So this could work. And this is how the first step in this algorithm. So this is the graph with some communities. So there are more links inside the communities than between those. That's the definition. And then we simply, first step is to divide this graph into two. Just randomly put nodes into one set or the other with 50%. So as a result, each community is divided into two parts, one at left and the other right. And then you can forget links inside these two sets and leave only links between those, and you get a bipartite graph. So these links are actually the internal links of the community. So this should be denser than those links. There are fewer links. And the algorithm is simply applying this argmin L to this bipartite graph. And the argmin, then the next step is to take only nodes that are in the argmin L. This is the bound. This is X and Y that minimize the L function. And the conjecture is that the only thing that happens is that some communities are completely absent here. So in this case, this brown one. And as a result, if you continue this, at the end you have only one community left. And in that way you can find all communities. And you don't have to know beforehand how many communities you have, because you find them one after another. Okay. Then a few simple experiments with D-Wave. So recently this leap system was opened in VTT in Finland also, and we used to test these things on this machine. So thanks to D-Wave. And synthetic examples are random bipartite graphs. So random bipartite graph, you have some probability, fixed probability, and for each node pair in this, you just flip a coin and draw link with probability P and do everything independently. And for this case, I just plotted samples of deviation of link density in subgraphs, and you can see that there are very few where you have large deviations. Mostly they are very small. So maybe that's the reason why maybe they are difficult to find. There are only, mostly you find these bad solutions. Okay, and this could be the solution, these extremal sets. Okay, first example is this real-life graph I get from Philip Vajo from Budapest. It's a directed graph that describes connection between cortical areas in the brain. So, and they used the regularity lemma, actually. They tried to find these regular pairs, regular partitioning. And I just took one regular pair that is described by this matrix. And there are only 18 nodes in this graph, just to test. And in this case, you can, of course, find make a complete search and find the exact solution. And the D-Wave was also able to find exactly the same solution. So in this case, everything works. Next, we did a bigger graph, 50 times 50 random bipartite graphs, so 100 nodes in total. But this time you cannot find the exact solution. But instead we use simulated annealing from the same leap system. And also here the answer was that both agree with the best solution. So maybe this was truly. But of course, here we have this problem of embedding. Using this minor minor fine embedding, we found that it is possible to have this kind of 63 times 63 nodes, but not all nodes are available, so only slightly smaller was possible to use. So this was the original whole bipartite graph. The links between are described by this, and this is the found subgraphs adjacency matrix. And the whole graph has density 0.2, and this extremal subgraph 0.3, so the epsilon is not too small. Okay, next I try to perhaps a bit more complicated case when we have a random regular graph, meaning that degrees are constant, 7 in this case, and similar, we get a very similar result. Both found correct the same best solution with simulated annealing and D-wave. And this is the whole graph, and this is the extremal graph. And slightly better epsilon, but not much. Okay. Then with simulated annealing, I tried a bigger graph with 400 nodes. And here you seems to have a degenerate ground state with almost equal energy. But the configurations are like complementary. So if you have here 0, then here you have 1. Quite strange that this happens. But I think in general, you can study this landscape of energies, perhaps. So this looks like there are two communities, almost equal type of communities. I don't know, this is hypothesis. Okay, so next I tried these community detections with two communities. This is one and the other is this. Here is the denser community. And again, with 100 nodes, both simulated annealer and D-wave found them 100% correctly. And with this simulated annealing, I tried a bigger with three communities. And again, it seems to work as I depicted. So these are the three communities. One is sparser and two are more dense. So at the first step, it took as an arc-min these denser communities. And then if you apply arc-min L to this, you find the one community. So again, 100% correct answer. Okay. By the way, for this case, for two communities, I have a kind of proof, at least sketch of proof that this should work correctly. Okay, so these are the conclusions or future challenges. So I don't know. Is this really this? Can you have from random bipartite graphs a hard instance of regularity check? Maybe this is too optimistic, but anyway, that's what I try to, or we try to do maybe next, and do these things. And also there are several conjectures in this community detection algorithms and others that probably we will go on. So is my time up? Okay, I have this, if it's time, I can show the appendix. Okay. So here are some proofs, but maybe this two community case. So what you get here is this kind of optimization problem with box constraints. And you can find the eigenvalues, eigenvectors, and show that one is negative and another is positive. And this is the box constraints. And this functioning of this algorithm means that the optimum is always in the corners. So you have a bilinear form and with box constraints, and in general cases, multidimensional box. And I think it's quite plausible that you find the optimum in the corners, because the eigenvalue with smallest eigenvalue with negative eigenvalue is outside this box. So like this, but I didn't finish this. So thank you. That's all. Yes.
So, time for questions. There is one over there.
Is your the objective function the same as modularity maximization?
Sorry?
The objective function, your community detection?
Yes, it's the L, the tau's function. Yeah.
Okay.
By the way, I think that the community detection is the easy case. It's not. There is a huge difference between this. That's my opinion.